Happy Valentine's Day, folks! And as a sort of way to celebrate today, I would like to discuss a special problem that I thought about just this morning when I woke up, and it involves three people in a relationship and planetary motion, and well, actually classical mechanics as well. Because right now in this video, I will be discussing about Marty, Jessie, lieu, and the three relationship problem. Alright, so here are the first assumptions we have to make in order to construct the problem. So we have three people, Marty, Jessie, and lieu, who are all attracted to each other, so they like each other, and they are in an open relationship of three people. So we can graph this as sort of three nodes, one, two, and three. And this Marty, Jessie, lieu, or any other babies, they're all related, connected. And this lesson is not only actually for this, but it's actually also an introduction to relationship theory, which is a new course at LOSC. Now, okay, let's make the following assumptions. If we let A1, A sub 2, and A sub 3 be functions that dictate the affection of these three specimens to each other, and if we let gamma be some universal constant that dictates the attraction between three members in relationships, and if we let F be their attractiveness, this essentially becomes a version of the three-body problem from classical mechanics. What is the three-body problem? So the three-body problem is basically a problem involving three masses with gravitational attractions to each other, something like this, and then we wish to know where they go given these initial conditions and their mass. The differential equation given for this problem is, well, if we put it in the notation of a while ago with lieu, Jessie, and Marty, we have A dot dot sub 1, A dot sub 1 dot double dot equals negative gamma F of A sub 1 minus A sub 2 over quantity A sub 1 minus A sub 2 quantity Q, or actually absolute value, minus gamma F A sub 1 minus A sub 3 over quantity A sub 1 minus A sub 3 Q. A double dot sub 2 is equal to negative gamma F A sub 2 minus A sub 3 over quantity A sub 2 minus A sub 3 Q minus gamma F times A sub 2 minus A sub 1 over quantity A sub 2 minus A sub 1 Q. Lower that so you can see it more. And then the last A double dot sub 3 is negative gamma F A sub 2 3 actually minus A sub 1 over quantity A sub 3 minus A sub 1 quantity Q minus gamma F A sub 3 minus A sub 2 over quantity A sub 3 minus A sub 2 quantity Q. And it's a system of equations that dictate now, actually this dictates the motion of three bodies subjected to each other with their own gravitational attraction to each other with masses F, actually, and the gravitational constant gamma. But in our case, this tells us the affection between the three members, and this is their general attractiveness, and this is their some universal constant that dictates the attraction between three members, two members, or whatever, members of a relationship. And so actually this problem has been shown to be unsolvable, or at least it cannot be solved by integrals. And there is a general solution that exists for this in the form of a convergent power series, but the power series converges so slowly that it's pointless, or it's very useless, honestly. It's not applicable for any. So what humanity resorted to is through numerical approximation. But what I'd like to do what I'd like to do is to break down the problem such that it becomes a simple form of systems of equations. So if we assume two members at a time, it essentially becomes an n-body problem, and so we can use arms races to model their attraction to each other, and it simply becomes a system of equation dot a sub 1 a sub 2 equals the matrix A minus B minus C D times a sub 1 a sub 2, which is the system A dot sub 1 a dot sub 2 is equal to a sub 1 a minus a sub 2 b d sub dA sub 2 minus a sub 1 c, and that's our system of equations. And this has a general solution, which is x equals c e to the at. You can turn your books to, if you have our parent material, which is elementary differential equations, you guys can turn your books to page number there's a page here. Arms races. Where is that? Arms races. Where is that? Values. It's somewhere around here. Non-homogeneous systems. Yeah, here. To page number 228, section 12.2, arms races. So it has a general solution. Yeah. Since this is a system, we already know it as a general solution. E to the AT, we're in A is this, because this is a simple so system of equations in the form x dot equals ax. Alright, and then A is just, well, this one over here. This matrix, this is x dot, this is x. C is some vector function that satisfies this equation. So there. It's actually that. So in our case here, x is c times e to the a minus b minus c d t. That's our general solution. And see some arbitrary constant, and that's actually raising e to this matrix is actually a very important thing in differential equations, because it dictates a spiral or a periodic solution to this system of equations. So basically, in order to break down the three relationship problem, we can take the members two at a time and then use this system of equations to solve it, or to dictate or to predict their behavior in each of at a certain time interval t. So that's it for the short video. Thank you for watching it. I'm gonna continue the lectures. Maybe tomorrow, maybe today. We'll see.